So good morning, everyone. Thanks for being on time. So let's get our third day started. Please.
Thanks, everyone. My microphone on? No. How's that? Better? Good. Thank you. So I'm going to try and speak quietly into my microphone because I'm afraid my voice is failing me a bit. So I shall mutter, and if anyone's too quiet, wave a hand and let me know so that I make sure you can all hear me. So I'm going to be giving the second of the three talks today, and what I'm going to be talking about is the GMTIFS instrument. So the first lecture was all about the general principles of sharp imaging with adaptive optics and wide fields with multi-object and integral field spectroscopy. And today I'm going to talk specifically about the GMT integrated integral field spectrograph, GMTIFS. So what I'll do is I'll quickly review some of the material from the last lecture, and then I'll look at the GMTIFS key science cases. I spoke a bit about that way. Good. So I talked a bit about some of the most important science cases in the first lecture. Here I'm going to be talking about what we call the key science cases, and I'll explain the difference between those when I get there. I'll then show how those lead to the science requirements for GMTIFS, and then how those in turn lead to the instrument design that we've come up with. And then finally I'll show you some simulations with a simulator that we have for GMTIFS, and how that can then feed back into evaluating how well we will do on some of the key science cases. All right, so these are our instruments. Today I'm going to be talking about GMTIFS down in the bottom right corner there. It's one of the two Australian instruments. It's going to be built primarily by the Australian National University, my own institution, and it's an AO-fed integral field unit spectrograph and imager. And of course the point of what we're trying to do is to get those lovely sharp images you can see in the bottom right and far right there, where we can get these very lovely high scale, very sharp images, taking full advantage of the 25-meter diameter telescope that we have with GMT. And as I emphasized in the first lecture, spatial resolution is key to most of these science cases. Exactly how well we can do and the trade-off between field of view and spatial resolution is going to be very important for many of the key science cases I'll talk about. Remember that we're going to be able to get a significant gain in angular resolution compared to the current crop of telescopes, so we need to push beyond that and see what it is we can actually do with that extra spatial resolution. And of course, we will also have the additional sensitivity that comes from our much larger telescope. And so we'll explore how that matters as well for many of these science cases. GMTIFS is very capable. It's an imager, it's a spectrograph, it's got integral field capabilities, and so not surprisingly, it can address many of the key science areas that the GMT is going to be talking about. I'm not going to have time to talk about all of the different science cases and all of the things GMTIFS can do, but I will try and highlight some of the ones that are, I think, both exciting and important for defining the instrument capabilities. And this is where we're going to get to. So the first half of this talk will be about how we came up with this particular set of science requirements. I won't do it item by item or bit by bit. We've done that in justifying the instrument to GMTO in the various reviews we've gone through. But what I will try and do is give you a flavour of how we go about looking at different science cases in order to derive some of the key parameters in here. So, for example, why is it that we've chosen 5,000 as the typical sort of resolving power that we want? How did we come up with the particular scales for the different spatial resolution elements in the instrument and so on? I won't do it completely, as I say, but I will try and pull out some of the more important things, which also have some interesting science cases. So in deriving the science requirements, the goal here is to explore those science cases which actually push the boundaries of the instrument in terms of its technical specifications. So we're looking for things that challenge the requirements. Now these may or may not be the most exciting things you can do. They may be somewhat niche, they may be in some other way special, but they're important for defining the boundaries of the instrument's capabilities. Now, the other thing to note is that some components in this argument are a bit arbitrary. There's the usual square root 2 issue with sample sizes. Every time you try and justify your sample size, people always say, well, couldn't you get away with something, you know, factor of 2 smaller, it's only root 2 in the noise or whatever. Those sorts of things are soft, and you just have to live with that. Another thing that's equally uncertain is exactly what signal-to-noise you need. Astronomers can argue endlessly about precisely what signal-to-noise is required in order to do things. So some of those things are left soft, and that's fine. Another issue to think about is the margin of safety. Some of the requirements are expressed with a low margin of safety built in. So, for example, the sky coverage typically is quoted in terms of the median seeing. Now that means that half the time you can't reach your specification, and that's not a good thing. So we need to think about what the safety requirements are. How much margin of error should we be building in? Should we be looking at, say, the 75th percentile for the sky coverage or something else? So these are things that you have to keep in mind when you're deriving the technical requirements from the science requirements. Another thing to keep in mind is that some design solution assumptions are necessary, right? I mean, we're going to have 7-8 meter mirrors. This is built in. Some other things are unnecessary to assume as well, and some other things are unavoidable. You've got to make some assumption before you can get down to details in any of the science cases. But, of course, we then need to go back and verify that those assumptions are indeed both required and sufficient. So the science case for GMTIFS has been through considerable evolution. The major science topics are intentionally aligned with the major science areas identified in the broader GMT science case. We're trying to figure out exactly what the science cases are that are going to have the most resonance with our very broad community. Remember, we're serving 12 institutions now with a very wide range of different astronomical cultures, different backgrounds, different areas of interest. So we need to have a very broad case. The conceptual design review document was the first version of this, and that was initially reviewed both by the broader community and by key experts from outside our partnership in order to make sure that it was hitting the main areas and not missing things. And that confirmed most of the key elements of the preliminary design, but it also highlighted a few cases where things had been overlooked and we had to go back and look at things again. There was then another active workshop in March of 2013, which again confirmed the span of the science cases, but the feedback from that introduced some new twists and some new sophistications to the cases that we needed to look at, and also ruled out some of the things on the wish list, either because it was decided that they were not essential or because they required the instrument to be distorted in ways that affected other aspects of its capability. This process will continue until the instrument is really being built. We will continue doing that, and right now, of course, as Rebecca said, the science case is being reviewed, and as new things are discovered, as the field progresses, that adds new things to the science case and tells us new directions that we might want to take. So we will keep on revising and developing the science case for as long as we can. As Rebecca, I think it was, emphasised, one of the lovely things about working with a ground-based telescope is you can use the latest technology. You don't have to freeze in your technology a decade or 2 decades before you actually have to use it. Of course, you can keep on developing it in future. So another thing you have to be very careful about is not designing out possibilities that may come out in future. If you can imagine some technical development and you think it might be valuable, it's best if you can design your instrument to allow that technical development to be added to or upgraded in the instrument. All right, so here's the GMTIFS set of science cases, and these are the key science cases that we use to define some of the technical parameters. I'm not going to have time in this lecture to go through all of these, but I will pick some of them and point out how they actually impact on our choices for the instrument capabilities and where trade-offs exist, why we've chosen one particular compromise over another one. The one area that we don't really address with GMTIFS is the dark energy, dark matter and fundamentals, but all of the others have multiple key science cases. So I think I've said that already. The other thing to remember is that GMTIFS is both an integral field spectrograph and an imager. So, we're not just designing an integral field spectrograph or just an imager, we're designing both, and we've got to make it one instrument. And so there's compromises and tensions there that wouldn't exist in a more specialized instrument. And so we've tried to come up with cases for both the imager and the integral field spectrograph. But you'll see that in some areas, our particular science cases do indeed include both the integral field spectrograph and the imager, but in other cases, it's just the integral field spectrograph or just the imager that's relevant, and so we need to keep that in mind too. All right, so let's look at one of the key science cases. And in fact, some of the key science cases are ones I discussed in the first lecture, so I'll skip over those and talk about some of the others. One of the ones I want to talk about now is the formation of galaxies, and in particular the formation of disk galaxies. And the sort of picture that is emerging now, and I'm going to do grave injustice to this field, so those of you who are expert in the field, please forgive me because I'm going to skip over all the details and try and get to the main point, is that disk galaxies have evolved from something that looked very unlike a disk galaxy in the very early universe. There are these clump cluster structures we see at high redshift, which are very lumpy, not ordered, not at all like the symmetrical grand design spirals that we see today. And the picture that we have, at least in broad outline, is of things like this gradually settling down and going through various stages where they form a bulge early on and then a very flocculent, lumpy spiral until we get to the mature spirals we have in the low redshift universe. And you can see just by looking at the redshift labels on this plot that this isn't an easy sequence, right? This isn't high redshift down to low, it's a bit lumpy, and of course different galaxies at different mass scales follow this sequence at different times. Nonetheless, this is the sort of broad picture that we're looking at. So the question is, what's the actual mode of formation for this? If that's indeed how spirals are forming, what is the underlying physics of what's going on? Is it simply a cold accretion, or is there some form of disk fragmentation going on as well? Well, there's certainly cold gas accreting onto a disk. That's undoubtedly happening. But obviously the disk was much more turbulent early on, and those fragments can actually that disk can actually fragment then into long-lived clumps. So here's some simulations by Bruce Elmergreen showing how these very large clumps, these very massive star clusters, can form out of this early, highly turbulent disk. The turbulence is supporting the gas against collapse. That's what's holding things up and leads to these larger clumps. So these clumps survive, they're not going immediately down to stars. And then the gas dynamical interactions lead to clump migration, moving in and out of the disk, mostly inwards, to form the secular bulge. Another question is whether there is simply cold accretion, if this is just a very cold, rapid collapse, or whether there is also a feedback mechanism involved here. And the question is, how can we tell? Well, steady infall, whether or not you've got some sort of perturbations on that form from interactions with other objects, does provide a steady impulse which keeps stirring the gas disk, brings you these higher dispersions in the gas, and that leads to these larger fragmentation scales and higher mass clumps when these things are forming stars. And so that's the basic physics behind why we see these clump cluster structures in the very early universe. Another point is that the gas inflow is clearly essential just to keep up the star formation rate, otherwise you run out of fuel. But the geometry of the flow turns out to have relatively little impact. It doesn't really matter exactly how the gas is getting in. The interesting thing is that the star formation feedback seems to help drive fragmentation and clumping on its own. The fact that stars are forming seems in a way that's not entirely clear at this point to help the fragmentation process and the growth of these very large clumps. And so the question is, what are the boundary conditions on that feedback? What is the broad nature of that feedback that's allowing this to happen? So one way of studying this is to look at lower redshift analogues of this process. And here are some observations that were done in natural seeing with an integral field spectrograph, Keck-Osiris, looking at this object, and initially with this local analogue indicated that there was a high dispersion gas disk. In other words, here was a galaxy that looked in the local universe rather like these high redshift galaxies that we're trying to observe. With the detailed observations that Keck-Osiris with AO was able to do, it was possible to confirm that indeed there was high dispersion and the star formation is very clumpy, but whether this was in fact a disk and whether it was really rotating was in fact less clear. So here are the questions that we'd like to be able to answer. What are the clump lifetimes for these giant clumps? Are they short-lived structures? Are they associated with significant mass concentrations? What's the physics driving the high dispersion in these disks, if indeed they're disks? Is it local pressure support, stellar winds, or supernovae? And then what about the ionization and metallicity and so on? The key to all of this is resolving the structures in question. That's where GMTIFS can come in. The spatial resolution required, if we look at these structures, both as best we can see them in the local universe analogues and in the simulation, is less than 500 parsecs. So that means in the high redshift universe, given that we've got this gift that angular resolution and physical resolution are essentially constant at high enough redshift, this means sort of 25 to 50 milliarc seconds. And then the second issue is the spectral resolution. Because it's high dispersion, it's not too challenging. 3,000 is sufficient in order to do that. It needs to be at least 3,000, but 3,000 would be adequate, so it's not too challenging. Another area that we can look at are all the things to do with stellar deaths, supernovae and kilonovae. Now these explosions you can see right across the universe, and the advantage with GMT sensitivity is not being able to see the explosions, because we can see them now with much smaller telescopes, but that we can see the conditions before the main release of energy and after the main release of energy. The onset of the stellar explosion, when there's only faint outer layers are visible, telling us a lot about the conditions immediately prior to the actual explosion, and the conclusion, when the inner structure and composition of the remnant is actually revealed. So GMT can address this both because it has high sensitivity and because it's got broad spectral coverage. We want to detect the near-infrared spectral features of hydrogen, helium, and the iron peak elements and molecules, but we also want to be able to resolve the structures that are going on, but luckily, because everything in these explosions is happening at high velocity, that means we only need very modest spectral resolution. The key thing again is the high angular resolution, and there we need it to separate the light around the remnant itself from the background light of the host galaxy, the environment in which that remnant is being found. So with the ability to reach up to 0.01 arc-second resolution, at 1 micron, we can actually probe the host galaxies of transients at a resolution of 50 parsecs when the universe is only a few 100 million years old. So that's an incredibly powerful gain that we've got by having this high spatial resolution with GMT. So here's an example. Here's an observation done with an 8-meter telescope, looking at a optical image of a supernova site, big blurry blob. The supernova is in here. Now, if you actually go to a higher res near-infrared image superposed, you can actually begin to see a bit of structure. The single cluster is resolved into multiple clusters there. Now, in fact, GMT will offer 17 times more spatial resolution and 80 times more sensitivity than these particular observations. So that's an enormous gain, more than an order of magnitude, nearly 2 orders of magnitude gain for this sort of science. Another thing that we should be able to do is be able to detect superluminous supernovae among the first stars that are forming. So this is first light, end of the dark ages science, with adaptive optics working out at 2 microns. we can actually see out to redshift 6 to 10 to get spectra for these superluminous supernovae. So it's SNSL, should be SLSN. The details depend a lot on the highly uncertain details of what these things are actually doing and how they're doing it. But for a range of reasonably plausible things, you can see that the capability is captured in this plot, which shows the observed AB magnitude as a function of wavelength. And you can see here the limits at different redshift ranges, different redshifts, 0.1, 1, 6, and 10, and at two different photospheric temperatures, 12,000 and 15,000 Kelvin, dashed lines for the lower temperatures. And you can see here, this is the limit for GMT spectroscopy and the limit for the GMT seeing here. And then with the adaptive optics, we get out to these limits here. And so somewhere between redshift 6 and 10, we should be able to still see these objects if they're anything like these models. And so that will open up a whole new field of study that's simply inaccessible right now. We can also look at the remnants left behind by more ordinary supernovae. If we're looking at intermediate redshifts, not 6 to 10, but 3 to 5 or so, then those galaxies are now about the right age to be starting to produce supernovae type 1a from the low mass stars in binary systems. Now, without adaptive optics, we could still, with GMTIFS, get spectra for supernovae type 1a out to redshift of about 1. But with the adaptive optics, we can push that right out to redshift 3 for the spectra, and for the imaging, we can actually get out as far as redshift 6. And this is a similar plot here. Again, the observed magnitude and wavelength. Here's a type 1a supernova spectrum at redshift 0.1, 1, 2, 3, 6, and so on. And you can see again where the limits are for GMT spectroscopy and imaging in the seeing and in the AO limits. And you can see we're getting out to around about a redshift of 3 at 1 to 2 microns. Another case that has been in the GMTIFS argument since the very beginning is studying the formation of the most massive galaxies. Here's an extract from one of the first things that Peter McGregor wrote, in fact, for the GMTIFS science case, way back in, this version is 2012, but in fact I think he wrote the original one in about 2010 or thereabouts. And it's looking at how the really massive galaxies form at redshifts greater than 3. The idea here is that these first light galaxies, the current generation observations can probe the formation of superluminous galaxies at high redshift. So we're looking at the very most luminous galaxies at first light out to redshift 6 or beyond. But these are very, very rare objects. They're certainly not typical objects. With GMTIFS, we can push down that limit to objects between 1 to 10 times L star. So we're getting down close to what we would consider a typical galaxy. This is competitive JWST for isolated sources due to read noise limits, but the real power is for extended lenses. And for that, we need to have extensive, i.e. high fractional sky coverage. Lyman alpha is the typical way that we've chased these things, but it's not always present due to the resonance absorption, and other lines could in fact be more important. Other lines are intrinsically weaker, but if you go to low enough metallicity for these first light galaxies, then in fact they may be stronger and may be actually usable. Here the critical thing is broad wavelength coverage. We don't know both what redshift these things are occurring at, and we want to get broad intrinsic wavelength coverage anyway. Yes, that's right. So the source... The background source. Yeah, that's right. Yeah, the background source is extended. Sorry, not the lens extended, yeah. Sorry, misstating it. Another interesting thing to do is to explore the use of gamma ray bursts as a way to probe the intergalactic medium. Here's an example of a gamma ray burst occurring at very high redshift, redshift 8.2. After 30 minutes after the actual outburst, it was 18 in the K-band, and 17 hours later it was around about 20 in the K-band. Now with GMTIFS, we should be able to get signal to noise of 50 per pixel at R of 10,000 at 18, K of 18, and signal to noise of 15 per pixel at the same resolution for K of 20. And so we can do, I hope, infinitely better than this extremely low signal to noise spectrum that you can see here, which was what was actually published in this particular case. The key requirements for doing this sort of science are, again, quite different. We need to be able to do a prompt response. That means we need to fire up the whole system, get it on sky, and look at something very rapidly. So that's an operational requirement rather than an intrinsic instrument property. The other key requirement is sky coverage. We need to be able to cover a lot of the sky. We don't want to not be able to get one of these vital sources simply because we can't find a suitable natural guide star or something close enough to allow us to get the target. And then we also need high resolution. Only moderate resolution for H1 stuff, but for the intergalactic medium, we want at least R of 10,000 or so. Okay, another area that presents a lot of challenges for GMTIFS is looking at black holes. We want to get in to see black holes in as many galaxies as possible and do Schwarzschild modelling of what's going on in there, in and around the black hole. So here are some observations. Here's some observations with GMOS, OSIRIS and VIRUS-P, looking at a couple of black holes around 10 to the 10 times the mass of the Sun. And here's one from Carl Gebhardt using NIFS, the integral field spectrograph on Gemini, looking at M87 and doing something, again, looking at a mass of a black hole, which is again approaching 10 to the 10 solar masses. The interesting thing when we look at these very high mass black holes is that there's a hint, at least, that they may be departing from the standard relationship between the mass of the black hole and the bulge velocity dispersion correlation. Here's the correlation, and you can see as you go to the highest mass black holes, most of the objects are sitting above this correlation. Now, this may well be a selection effect, and I don't want to get into all of that, but it's intriguing to consider this possibility, and so we'd like to be able to look at many more of these objects. That means we've got to be able to look at a big volume, because we're looking at the extreme end of the massive black hole mass distribution, and that means we need to be able to do very high resolution imaging out over a very large range. So, restating what I've really just said, spatial resolution is key. We want to be able to get beyond, the nearby clusters where we've been looking so far. The volume increases rapidly with distance. There's a surprise. There's a trade-off, however, between image quality and sky coverage. We want great image quality, but we also want to get very high sky coverage. These things are relatively rare, so we don't want to be limited in which bits of the sky we look at, but we know there's a trade between those two things. We can't cover every bit of the sky because we don't have bright enough natural guide stars. So high image quality gives us greater distance, more volume, but better sky coverage allows closer targets and better data. We also want to be able to work at short wavelengths. Once we lose the CO lines, we need to use the calcium triplet. On the other hand, the spectral resolution requirements are relatively modest. One thing, however, we do require is good stability. We want to be able to do long integrations over multiple nights, and we want to be able to do good cross-correlation between our observations and the template library. So that's a key stability requirement there. Another question is, what about intermediate mass systems? So here's a little table showing the mass of the black hole, the radius of its sphere of influence at different distances, and what resolution this actually requires. And as you can see, at 2 megaparsecs, things are relatively easy. At 10 megaparsecs, it's beginning to get more challenging once you get down to the lowest mass black holes. So to look at the other end of the black hole mass velocity dispersion relation, we need to be able to access a bigger volume than currently can be reached with the 8-meter telescopes. That means we need both spatial resolution and spectral resolution, because now we've got, of course, much lower velocity dispersions in the objects around the black hole. Oh, of course, no, there's it twice. So, in a very different field, another thing we'd like to be able to do well is angular differential imaging. So the basic principle of this process is to turn off your derotator on your Alt-Az telescope and smear out your star. Let the natural rotation of the sky with an Alt-Az telescope smear out the star. And then you get an image that looks something like this. There's an occulting disk here, and then this is the rotator image. And what's being done there is a large number of very short exposures have been co-added, each with taken at a different rotation. Then in panel B, you angularly average that and subtract away the angular average image to get the resulting speckle images here. And then this image is just that image, but with a bigger stretch in the intensity plotting. And then you re-rotate all your different images, which were all taken out of sync. And when you do that, you're incoherently adding all those speckles together. And so almost all the speckles go away. And as a result, you actually vastly reduce the number of, the amount of halo from the speckles. And in fact, when you do that, when you co-add many of those images, you can actually get down to something like this. This is at the same stretch of that, but is 100 odd images co-added. And you can see that you've further reduced it basically at the Poisson rate. Now, the first measurements have been done like this with AO systems that haven't been optimized for this sort of observation, right? They're just general purpose AO systems. The point is that, that allowed us to figure out what an optimized system for doing ADI would actually be. People are now building those instruments. But there is still a possibility that with a general purpose AO system like GMTIFS, we could still do some of the same science that the optimized ADI systems could do, provided we can get it on sky early enough. Now, likely we won't push the inner radial boundary, but that big light-gathering power means we can probe to fainter systems at large radii and do some direct spectroscopy. All right, so here's just an example. I showed this movie actually in the first lecture, so I won't show it again here, but it just shows the sort of power that exists in this sort of technique doing exoplanetary imaging. Okay, so that was the quick run through some of the key science cases. Now I'm going to talk about how we go from that long list of here's a science case and here's what that science case requires to actually turning those science requirements into technical requirements. So here's just a very top-level summary of where these different areas basically drive the technical requirements. So galaxy evolution is a good source. There's a whole bunch of what you think of as workhorse programs, right? They don't really push the boundaries, but there's a huge amount of science that you can do in the broad area of galaxy evolution for both the integral field spectrograph and the imaging. And those drive lots of the basic operational requirements, and things like, the minimum spectral resolution and how quickly you can change things around and so on. The first light and reionization case, there the thing that was really being challenging was the sky coverage. You want to be able to cover as much of the sky as possible, and you also want to be able to do things in target opportunity mode, not model, target opportunity mode. And when a GRB goes off, you want to be able to quickly fire up your system, point at the GRB, and get some good data. The black hole science case, the things it really pushes are the AO precision, the spectrograph stability, and also your acquisition procedure in detail. And with exoplanets, there's some operational challenges about, how we actually implement the ADI. And then, in fact, there's some other things to do with, if you want to look at near-Earth objects in the solar system and so on, you've got to worry about non-sidereal tracking and things like that as well. So let's look at those in a bit more detail. Here are the extragalactic science case requirements. For wavelength range, the emission line requirements drive you to very broad wavelength range. You really want to cover as big a wavelength range as you possibly can. You want to look at a broad range in the intrinsic spectra, and you also want to cover a broad range in redshift. Sensitivity and volume coverage means you're really looking at intermediate resolution, 3000 and up. Image quality, largely it's not too challenging. If you can do as well as the 8 meters, then in fact for most of the extragalactic stuff, you're not doing too badly. Sometimes you want to do better, but it's not really a major driver. Most of the structures you're interested in are actually being resolved already. But you do want high encircled energy. You want to drive the sensitivity, so you want to get the most light down the core of your point spread function as you can. And again, you want good sky coverage. Interestingly, it's not obvious that the 80% requirement that was specified is really essential, but on the other hand, real survey fields are not usually the median statistic. And the really big challenge is lensing. We want to be able to get the very best lenses, so we don't want to throw away that golden lens opportunity just because it's not well set up for, typical, it's not in our sky coverage. Another issue is just the operational one, observing blocks. We want a good duty cycle. We typically want 2 to 3 hour observing blocks, that means. And acquisition and relative alignment limits are also challenging, but I won't get into those sorts of really grubby details. Then there's the high contrast imaging, so challenges for ADI and spectroscopy and so on. Here, one of the intrinsic challenges is our segmented pupil. There's not a lot we can do about that. We're pretty much committed to that, I think, at this point. Rebecca, is that correct? We're not? Okay, all right. Can't change that one. So that means we've got to be able to deal with the bright secondary maxima that occur in the point spread function out to quite large radii. We'd also like a wide range of occultation, so that means, we've got to assume there's a design solution and there's other requirements, minimum opacities, angular size, and so on. It's a semi-transmissive system that aids alignment, but there's still some concern over ghosting, which impacts on our sensitivity. We've got to really understand our stray light issue. The black hole science case, again, needs all instrument modes. You both want the imager and the spectrograph. You want high spatial resolution. As Rebecca was saying to me in the bus coming over this morning, those black hole guys, they just want all that spatial resolution and then some. They're never satisfied. But we also want a wide field of view, which pushes, of course, for lower spatial resolution. We want excellent relative sensitivity. We want a range of resolutions to do both the high mass and low mass end of the range. And the imager can provide some really vital data. So we've got to have the imager as well. It is challenging operationally because of the duty cycle, because of the acquisition requirements, and again, the AO requirements. And then there's a bunch of stuff that impacts the requirements for the technical requirements for the instrument that come from things outside the science case, that come from other aspects of the telescope that we need to keep in mind. One of them is the deliverable image quality is affected by things like vibration at the Gregorian instrument rotator focal station. There's the adaptive optics performance, which is not within the instrument team's control. There's the optimal integral field spectrograph scales for short wavelengths. That's affected by what's actually delivered in the images. And then, of course, there's the endless arguments about the imager trade-off between pixel size and field of view. So we're offering a range of those, but no matter how much range of those you offer, someone will claim they need something else. In terms of sensitivity, another thing we're talking about in the bus are the mirror coatings, the thermal and sky emission that's affected by whether or not you've got an open or closed top end, the sizing of the secondary mirrors, and so on. And then there's sky coverage. And that can be critical in some of these areas, right? As I said, being able to do adaptive optics over more of the sky really helps in at least some of these science cases. And then you've got things like tracking. Tracking affects how long you can expose for when you're doing ADI. It also puts restrictions on what solar system objects you can observe. There are some solar system objects that are just moving too fast that we will not be able to track with GMT. It's too big, too heavy, not going to be able to do it. We want to have a targeted opportunity mode, and we want to have a triggered mode where we can go, bang, something's gone off, fire it up right now, drop everything you're doing, get that telescope pointed to this part of the sky. And then we also want regular monitoring programs where you need some sort of Q mode observing in order to fit things in. Then there's operational concepts. How do we actually do acquisition? How do we do handoffs between different subsystems and dull stuff like that, which affect, quite importantly, how the overall performance is perceived by the end users. All right, let's talk about some of these in a little bit more detail. Sensitivity, for the mirror coatings, we want minimum reflectivity loss between recoatings. We would like tertiary coating and cleaning. All of these things you obviously want the highest performance possible, but of course that impacts how often you've got to recoat the mirrors, how often they're cleaned, etc. And these have operational impacts which are going to be decided not by our instrument team. The thermal emission, the top end structure is open to sky in K but closed off in J and H. Okay, so that has different implications in the different bands. No significant tension, however, between the requirements affecting sensitivity. There's not a trade-off between these particular things. You want to optimize all of them, but they don't affect each other, so there's no direct tension there. For image quality, there's a whole range of external factors. There's operational things like target acquisition and reacquisition. How long is the minimum observing block? That affects duty cycle and efficiency. There's the AO performance model, and the question is, what precision do we really need to achieve? There's the optimal suite of pixel sizes and field sizes for the integral field spectrograph, and also the similar question, what's the best imager pixel scale and what field of view can we achieve at that scale? We have to worry about atmospheric dispersion compensation, both within exposures and between exposures, and also the impact on repeatability. There's also a technical issue about the impact on the autoguide wavefront sensor as well. And then there's the nightmare of vibration, and I've seen how this can affect things badly when it's done wrong. We've got to worry about other instruments, the Gregorian instrument rotator table itself, transmission of vibration from other instruments, and what, of course, we actually generate within GMTIFS itself. So there's a vast array of all these factors that need to be kept in mind. In the sky coverage, one of the things that Rob Sharp often emphasises is that there remains a bit of a disconnect between the assumptions in the current science requirements and the actual specifications for the laser tomography AO. So the science requirements we've got as the instrument that's mostly using the AO and what's actually being specified for the AO system still aren't quite well aligned. And the high strail skies coverage is still the most problematic thing. It's the thing that drives us. We want more sky coverage, we want more strail, and getting the tension between those tuned just right is still a controversial point. The current goals are that with natural guide star AO, we're looking for a K strail ratio of 0.75 or better for a V of 8 guide star. With laser tomography, in the H band, we're looking for a strail of 0.3 or better and at least 20% sky coverage. With the encircled energy in the K band in 50 milliarc second pixels bigger than 0.4, we want to achieve at least 50% sky coverage. And with 85 milliarc second pixels, we want the encircled energy greater than 0.5, full width half maximum less than 20 milliarc seconds for a K of 15 guide star. And so this is a complicated parameter space that we need to negotiate. Here's an example showing you what sort of sky coverage we might actually be able to get, for example, in the HST Chandra Deep Field South. So here on the right, oh, bother, keep pressing the forward button instead of the laser button, you can see the 90 arc second coverage, the 60 arc second coverage, and the 30 arc second coverage that we get for different K-band limits, and you can see those fields translated in the same green and blue colours over here on this side, and you can see what targets you can and cannot get within the HST Chandra Deep Field. And so you need to look at that for a large number of science cases in order to figure out whether you've found the sweet spot for a given science case. Okay, so I think I've actually talked about some of this already, but the targeted opportunity programs are assumed to be possible. We're simply going to assume that that's a mode that GMT is going to offer. It's really essential for the exciting GRB work I was talked about, and indeed for other things where there's a very rapid response required, and an obvious case there are sort of kilinovae and things like that. This does require a rapid cold start of GMTIFS and the LTAO systems, and that could be challenging. Monitoring programs, they don't need that rapid cold start. You know when you're going to be doing your observations, but you need to be able to respond by optimizing your observations to the particular conditions. You'd like to have some ability to choose on a night the bit of time when the seeing is really good, so you can get that great AO response. They need the spatial resolution of GMT, but they don't really need the sensitivity. How do you predefine the observation set? Something we need to figure out. And we're assuming that there's some sort of Q mode to support this monitoring over an extended period. So when you take all of those and a myriad other science cases and considerations into account, you do end up with this set of science and technical requirements for the instrument. It is a set of compromises, but it is, we believe, a good set of compromises that allows almost all the important science to be done effectively. Okay, how then does all of that feed into the instrument design? So here's a very early block schematic that Peter McGregor came up with. You're not meant to read any of the details here. You're just meant to appreciate that one way of thinking about an instrument is not to think about optics or any technical things whatsoever, but simply to think about the things that need to be done. How do things get done? You don't have to worry about how any bit is done, but you do need to think about all the different things that you need to do in order to get the image or spectrum that you require on your instrument. And block schematics like this are a good way of doing that thinking uncluttered by all the details of how you do things. On the other hand, you also need to think about how you're actually going to implement the optics and everything else. And here's a very early sketch of the light path for GMTIFS. We have improved on the methodology involved here, but nonetheless, scribbling things on bits of paper is how science still gets done when you're first thinking things out. So these are the specifications that we've come up with. In order to meet those science requirements, these are the very top-level specifications of the instrument. So we've got an integral field spectrograph operating in the near-infrared. It's image sliced. It offers a field of view of 4 by 2 arc seconds when you have the large 50 milliarc second pixels. And then there are 3 finer scales, basically halving that 3 times, 25, 12, 6 milliarc seconds, with proportionately reduced fields of view. The spectral resolution has 2 modes, 5,000 and 10,000, and we're using VPH gratings in order to make this as sensitive as possible in order not to lose throughput. The wavelength range it will operate over is 0.95 to 2.5 microns, so we're doing the whole of the near-infrared, JH and K windows. The imager, also operating in the near-infrared, has a 22 arc-second field of view, and this is matched to the expected corrected field with the secondary mirrors that are going to be able to do the adaptive optics. We're going to have 5 milliarc second pixel sampling matched to the J band, so where we do best. But this is relatively fixed format. We don't have all the options that we do with the integral field spectrograph. The detectors that we're going to use for this are for the integral field spectrograph and for the imager. We're going to have a Hawaii 4 array with 15 micron pixels for the IFS and either 10 or 15 micron pixels for the imager. And then we also have an on-instrument wavefront sensor that we need to do to complete all the adaptive optics and other things that we need to do to make it work. And that's either going to be a couple of Hawaii 2 arrays or possibly something that we're exploring at the moment, these electron avalanche photodiode systems, which are very attractive for adaptive optics because they're effectively zero read noise. The atmospheric dispersion compensator is also something that's going to offer full correction for both the imager and the integral field spectrograph and allow simultaneous observation. So the project has been going for quite a while now. There was an original competitive conceptual design review process which was reported on back in 2012. It was GMTIFS was then selected as a first-generation AO instrument. The plan is to commission it in 2023 or 2024, telescope permitting, and to offer it with all of natural guide star, laser tomography, and ground layer adaptive optics modes. The preliminary design study has been going now for 4 years. It will finish this year. The aim has been to first refine the science requirements, what I've been talking about, to do a full preliminary design, but also to try and remove some of the high-risk components as well. In particular, the optical design, which is challenging, the integral field spectrograph camera optics, the cryostat design, the many mechanisms. Dan is talking about his lovely zero mechanism system. Oh, how I wish I had his zero mechanism system. We have lots of mechanisms, many, many mechanisms, and many of them have very challenging requirements for stability in a cryogenic environment. There's the detector system development, the EAPDs I was talking about, and the adaptive optics beam steering mirror, which is one of the very challenging movable components. And then, in fact, the other thing that's been folded into this is we've also taken on the on-instrument wavefront sensor. That was appended to the instrument program in 2016, and we've been doing some studies of deformable mirrors. All of this is building on instruments that we've built before. I'm trying to reassure you, having worried you with all the difficult things that we're doing, that we've got this. We do know what we're doing. We have built similar systems in the past. We've built a adaptive optics infrared, but also integral field spectrograph for Gemini, the NIFS system that I hope many of you have used. And we've also built the adaptive optics imager on Gemini South, which is currently being used with the GEMS multi-conjugate adaptive optics system. So we do have a record of doing this. Both of these instruments work very well. And we've actually built another system on our own 2.3 metre telescope, the WIFE's optical integral field spectrograph. So we do have significant track record in this area. Here's an example of the sort of thing that GSAOI and GEMS are able to do. Here's the antenna galaxies, the classic HST WIFPIC2 image, and here is the GEMS image that's obtained with the MCAO adaptive optics, and you can see that the system works very beautifully. Here's another example. Here's a galaxy cluster at a redshift of 1.07. Again, comparing ACS this time, HST ACS in the I band with Gemini and GEMS in the K band, using the fact that the K to I band is 3:1, which is roughly the same ratio that Gemini Advantage has over HST or GMT and JWST. Okay, so a lot of the science is, of course, with the integral field spectrograph, but the imager is, a science instrument in its own right. It's going to be used for a bunch of very significant science, and has some particular problems of its own. We've got to worry about target acquisition. This is really critical for fast transients, right? When we're going to get on that GRB or that kilonova or whatever, we don't want to be mucking around with a very long and complicated target acquisition process. So we need to come up with something very quick. That means it's got to be fully integrated with the GMTIFS control system and with GMT. The response time is actually likely limited by the telescope. The slowest part on the critical path for doing acquisition is the 3-minute slew time for the adaptive optics system. The guide star access for the central science field is also important. We're going to have some on-detector guide windows. I was talking earlier about the segmented pupil. Here is the actual pupil that we're looking at for the mirror. So this is the nice clean outer secondaries and the strangely shadowed central secondary. And this is the resulting point spread function that we expect to get. This is actually done in monochromatic light at the moment, but we're planning to do some polychromatic simulations soon, and the instrument component needs to be included in this. This is just the GMT, and we need to put in all the impact on the point spread function from within GMTIFS itself. Here's the basic layout and design. I'm not planning to go through this in any detail. As you can see, it is quite complicated. Because it's both an imager and a spectrograph, it's got a complicated light path. It's got the tilted dichromatic windows at the front, science pick-off here, off-axis parabolic relay, collimated beam, ADC and cold stop. Then you've got the imager arm, that's on an image R arm, that's an imager arm. And then you've got the integral field spectrograph with the scale selection and anamorphic projection, and then the image slicer, grating turret, and the refractive camera back in there of the integral field system. There are a lot of moving parts. There's a long list there, and they all have to work, or most of them have to work in a cryogenic environment. So this is a challenging system to build. We have been working to try and remove some of the challenges. So some of the pictures that you've been seeing have shown GMTIFS as this semi-triangular sort of structure. That was the original concept design review baseline structure. We have actually come up now with a cylindrical cryostat with 2/3 the size, which still keeps the three-layer structure that makes it easy to get at, but it's much less massive, cheaper, and easier to cool. And so, cylindrical cryostats are easier to build than triangular ones, so this is a much improved system. So that's what we're now actually looking at. And we actually have reserved some volume in there, although it's not shown, for the on-instrument wavefront sensor sitting there. Here's that cylindrical cryostat. The mass budget's about 1 tonne for the cryostat, 1 tonne for the instrument, and it'll be located, as you know, at one of the folded Gregorian instrument rotator ports. Both the natural guide star adaptive optics and the laser tomography adaptive optics wavefront sensors will be hosted in the cryostat. The packaging of this is a challenge, fitting everything in, but we believe we've essentially solved the problems for that. And here's the physical layout in a CAD rendering. You can see all the elements I talked about. I'm not going to go through them all again, but you can see the table layout for the system there. It's quite compact now, but with a significant number of folds. One thing that is worth talking about is the refractive camera for the integral field spectrograph. Originally, we had a 3-mirror anastigmat camera design, but that was considered too risky, so we've gone to a refractive camera design, which has also allowed this cryostat size reduction. There are only 4 elements, but they mostly have some challenges. I won't go into the details there, they'll only interest the optical designers amongst you, but that's the system that we are now going with. The current throughput estimates with that new design are shown here. This is the throughput of the instrument itself. It excludes the telescope, the atmospheric transmission, and the detector QE, but the spectrograph itself and the imager are producing throughputs in the 0.3 to 0.4 for the integral field spectrograph and the 0.5 or thereabouts range for the imager. I think I'll skip that one. One of the big challenges, however, is the beam steering mirror. This is the really critical element and most challenging element for the adaptive optics within the GMTIFS system. And it may actually turn out to be the first element of the adaptive optics system that actually gets made. It's currently being tested for surface figure and roughness and the mechanical control, which is very challenging because of the very tight tolerances and the high dynamic range required, all of which is, of course, occurring in a cryo environment. One thing that's important for operational purposes is looking at the GMTIFS field. The outer field here is the 180 arc-second diameter field that's actually passed by GMT, and that's undergoing partial correction by the correcting secondaries. The 60 arc-second diameter LTAO asterism is shown here. So this is the asterism produced by the laser tomography AO system. That's externally reflected to the laser wavefront sensor. And then within that, there's a 22 arc-minute square field, which is the imager science field. And within that, again, is the 2 arc-second by 4 arc-second integral field spectrograph field when it's working with the 50 milliarc-second spaxel sail. So this is the configuration we've got. Here's our natural guide star somewhere within that outer field, the inner field for the laser tomography stars, and then the 2 science fields within that. The AO system is spelt out here in a little bit more detail. The spatial, not the spectral guide field, is split. the external natural guide star LTAO system, and then we've got a on-instrument wavefront sensor tip, tilt and truth system. That's happening actually within our instrument. There's a warm optical system, the active M1, the adaptive secondaries, the pupil steering M3, first two coated with aluminium at first light, the M3 coated in gold, and then a single warm cryostat dichroic pressure window calcium fluoride. There's no independent AO feed. The instrument is integrated into delivering the AO corrected field. Natural guide star, you've got an external optical system, LTAO, also external, but expected to be something that we may be contributing to as well. And then there's the GLAO system, which is the default mode for telescope phasing. Here's the ground layer adaptive optics system. I think I may have shown this diagram before, showing the performance, the delivered full width half maximum expected as a function of wavelength. This will be the early commissioning mode for GMTIFS before the rest of the adaptive optics system is required, because it has minimal dependence on the AO wavefront sensor components. Okay. Yeah, so natural guide star adaptive optics. The AO simulations we've been doing for this mode, we're actually not using the median, we're using the 75th percentile used for our baseline. Instrumental wavefront error budget appears to be achievable. It's challenging, but it's tractable. There's some non-common path correction, which has been offloaded onto the adaptive secondary mirrors. And then there's slow flexure correction using the on-instrument wavefront sensor. And we require a K-band strail of greater than 75%. And in fact, we show that with a 8th magnitude star, we can actually achieve 89%. And at 12th magnitude, we're just about meeting this requirement. So it looks as if for anywhere where there's a 12th magnitude star or better, we can actually do this just fine. The laser tomography adaptive optics is an on-axis field, an off-axis guide star with its own deformable mirror, so effectively multi-object adaptive optics. Again, we're doing the wind shake, allowing for the 75th percentile. Our goal is to achieve a strail ratio in K of better than 0.4, and there's a trade-off between sky coverage and that strail. So here is the strail requirement of 0.4, and you can see the off-axis distance we can achieve at that strail ratio for different limiting magnitudes there. In the H-band, the requirement is that we've got a strail ratio greater than 30% for 50% of the sky at the galactic poles. And simulations indicate that in fact we will achieve something more like 80%. So here we're easily beating the nominal requirement. So that's a very positive outcome. Now, these simulations I'm talking about are actually done with a very detailed instrument simulator called GMTIFS Sim, which is actually based not on the NIFS or GSAOI instruments, but actually on the much more modern simulator that we have for WIFES, our own in-house integral field spectrograph on the ANU 2.3 meter telescope here. This is WIFES here. This is a system called PyWIFES. We've hacked that system in order to turn it from a data reduction system into a simulation system for GMTIFS. It includes a very detailed simulation of the instrument. So here's some delivered images after running through the simulator. It simulates all the different properties. Again, you don't need to read any of this, but you need to see that in fact, we're simulating all the structures that are actually in the object in order to produce the most detailed possible images. Here's the point spread function and the spectra that are delivered. And you can see that it's a very detailed simulation. It also allows us to simulate the acquisition process. Here's the natural guide star and the probes and so on and so forth. So it's a quite detailed model for the instrument. Come on. There's some simulated data. That's imager data showing what we can get. Not a very interesting image, I confess, but shows that we can do it. And it also allows us to step through an actual sequence of observations. So we can set up a pretend set of observing blocks for the instrument. So overall, this really allows us to understand how we can actually operate this instrument and what it really delivers in detail for GMT users. So here's an example. Here's an object from the ultra-deep field at a redshift of 1.5, just an interesting cluster-type galaxy here. These are some VLT symphony observations that were taken. I'm not really interested in the observations here per se, but just to show that we can actually simulate what this would look like taken with GMTIFS. We actually put in some the observations from the ultra-deep field, and then we try and observe that using a real setup with a 9-hour integration on source, 3 hours off, RF 5000, 50 milliarc-second pixel scale, and you can see what we get. There's a movie showing what we look like as we step through the channel maps. Here are the individual channel maps on the right, and you can see that this is the image that I used back in the first lecture to show what it was that we could do. And that image isn't just a fake simulation. That's run right through our entire optical chain and all the data reduction, and so should be a very good indication of what the instrument will really deliver. So there it is at a bit more simulation now at the 25 milliarc seconds per spaxel, 4 times the resolution of JWST, and you can see what we can actually get out of it. And there's a bunch of different science that one can derive from these things. The point I wanted to make here, though, is that we are trying to do very precise modelling of what this instrument will actually deliver. Here's another case, another very challenging Gemini Genius observation, 29 hours at RF 320, very low resolution. And this is the spectrum that you get from that here, okay, up to 29 hours on Gemini. That's the actual NICMOS image of the source on the right. Here's what you get if you run it through GMTIFS you can actually split it up. Because you've got an integral field spectrograph, you can look at this is the spectrum you get within RE of this image. Here's the spectrum you get out to 2 RE, and even between 2 and 3 RE, you're still doing a better spectrum than Gemini was doing, integrated over the whole thing. And this is done with 14 hours on source, the actual source profile, and some other details. Last example, here's a MHD simulation of a jet coming out of a galaxy, some work done by Jeff Bicknell showing the O3 luminosity at a certain stage in the jet's evolution. We then use that simulation, put that into our simulator as if it were the on-sky truth, and then we can show what we would actually see from the integral field spectrograph here. You can see again, this is the mapping of the O3 line intensity over that thing, and you can see that we're recovering this crown structure in the actual jet. So again, if you can provide us with simulations of what you expect to get, not just on sky data, we can actually simulate what GMTIFS should be able to see for you. So that's it, that's all I've got. But on a mountaintop somewhere near you, one day, you will have access to this wonderful system, and I'm sure you'll do some great science with it. Thank you very much.
Questions? Let me do a question. You mentioned sometimes the duty cycle.
Yeah.
Can you explain what that is for the audience, please?
So this is the amount of time you're actually spending on the source compared to, moving between sources, or indeed getting the adaptive optics acquisition up and running on the source. So it's simply the live time on source that actually goes into the integration number that you calculate for your science. And all the rest of it is dead time, that you're not getting any science done. And we're trying to, in all the many different modes that we offer here, we're trying to reduce the dead time and make that duty cycle as high as possible.
So what fraction of the total telescope time we are actually point to the target with this?
So typically, you're losing, for all the long integration things, it's trivial, right? So for example, that example I showed you of the UDF thing, that was 9 hours on the target, 3 hours on sky, so that's science time as well, it's not dead time, you need to do that. And the actual overhead on that was actually less than 5%. But for other cases where you're, doing a cold start of the system to go and see a GRB and you want to take a very short exposure, you might have a, 15-minute exposure of the GRB, but it might take you half an hour to get up and running, and so suddenly it's not very efficient. Now, of course, that's not something you're going to do a lot, but there's a huge range depending on the mode in which you want to do the observations, what sort of AO you want to do, and so on and so forth. So it's a hard question to answer, but one that the simulator, if we've correctly estimated what all these critical path things are, can tell you for any observation that you care to dial up.
Other thing that caught my eye was the efficiency table you put there. So what struck me is that there's not a lot of difference between the spectroscopic modes and the imaging mode. Is that because the image slices are so efficient?
Yes.
Or the imaging is somehow not as efficient as it should?
The integral field spectrograph is very efficient, and so you're only losing 30 to 50% light relative to the imager. The gain of the imager, of course, is that it's got even smaller pixels and an even bigger field. So there is a loss of field coverage, so you're losing light in that sense. But in terms of photons going through it, yes, the integral field spectrograph is very efficient.
More questions?
I have several, so I'll just focus on the nasty one.
Oh, good. Thanks. You don't want to leave that one for later and ask me the easy one here.
Sure. As you yourself emphasized, the instrument has a lot of moving parts.
Yes.
Which made me think, for maintenance reasons, you have a huge a system that you're supposed to warm up, then operate, to maintain and cool back. So how long does it take to warm up or cool down such a big system?
Actually, I don't know what the number for that is right now, but it is long. I mean, this is not something you're going to do often. We're designing it so that the maintenance cycle is 3 to 5 years, not something you need to do monthly or even yearly. So in theory, I think breaking, 3 to 5 years is the maintenance cycle.
And of course, related with the moving parts is the issue with the stability of the system, and therefore how easy it is to write a pipeline, data reduction pipeline for this.
Yes. So we are, of course, in the simulator, assuming that everything is as stable as the specification. Reality, may differ. Your mileage may differ, as they say. So, but we are working very hard on that because stability is so critical, not only directly to some of the science cases, but also, as you correctly point out, to the ease and precision with which you can do the data reduction. So we are spending a lot of time on that. And that's why we're doing so much prototyping, particularly of the mechanisms. GMTO have been very worried about the mechanisms and have made us do lots of extra testing, and I think they're absolutely right to do that. I can have no complaint. It's the sort of necessary rigor that's required for this system.
Thank you.
Oh, hi.
Most of your science cases require large sky coverage. I wonder about the operational implications. You need to use laser stars. What is the implication, for example, for the environment, for flights? Because this is a region of the country, Chile, where there are lots of airplanes passing, and I wonder if these lasers doesn't affect it or have an impact on it.
I'm going to hand that one off to Rebecca.
So there are lots of there are lots of telescopes already using laser systems, and what they have actually is constantly evolving for keeping airplanes safe. So they used to have spotters that they kept outside that were looking for airplanes and keeping track of where the lasers were. So you had people outside all night, and you had to get approval for any location in the sky that you were going to point. So there had to be an interaction with governments and with the flight regulation, flight control. honestly, that whole process is evolving so quickly. I don't know how we'll do it in the future, but it is already done now, and it's only going to get easier.
Okay, that's interesting because this adds another saving the budget of the telescope time available for all positions in the sky.
Well, I urge you, if you just Google lasers on large telescopes, what you will find is an amazing array of gorgeous pictures of laser beams shooting out of telescope domes at the sky. You see them at the VLT, at the Gemini telescopes, and at Keck. And we don't yet have a laser system at Magellan.
It's really not a problem. And in fact, it's not just astronomical telescopes. So at Mount Stromlo, we also have a company that does laser tracking of satellites and space junk for NASA and JAXA and the other space agencies. And they're actually a much bigger problem because they're using a higher powered laser than we use, because they're actually bouncing things off things in orbit 1,000 kilometers up, not just 90 kilometers up. And they're zipping around all over the sky. They will have 1,000 different positions that they will look at during the night. And so they can do it, and they do it all the time, and they're doing it for the government, so they have to be very good about the regulation. And they're a much more challenging use case than the astronomers. And they've figured it out. So I genuinely don't think that's going to be a problem.
If I could add one more thing that's just sort of fun. If you've ever observed at an observatory where there's more than one telescope and the other telescope has been using the laser system, I think it's actually more interesting how the lasers interfere with local observations. So if you're observing on Keck 1 and Keck 2 is shooting a laser anywhere near your field of view or across your field of view, you sometimes see excitation in the atmosphere from that laser. And so I think it will be important at Las Campanas to coordinate this and be considerate of our neighbors.
Of course, being the biggest telescope, we get first rights.
That's just not a popular opinion.
Star Wars.
More questions? Okay, if not, let's thank